Hi everyone, so I'm here to do another AP Physics C free response. This one is from 1990 and it's electricity 2. The figure I would redraw, but it's kind of complicated, so I just figured we could just look at the diagram on the paper, and I'll just read the question. In the mass spectrometer shown above, particles have a net charge plus Q, are accelerated from rest through potential difference in region 1. They then move in a straight line through region 2, which contains a magnetic field B and electric field E. Finally, the particles enter region 3, which contains only a magnetic field B, and move in a semicircular path of radius r before striking the detector. The magnetic fields in regions 2 and 3 are uniform, have the same magnitude B, and are directed out of the page as shown. A. In the figure above, indicate the direction of the electric field necessary for the particles to move in a straight line through region 2. Okay, so the direction of the electric field is to the top, as you can see on the paper. Reason why can be shown by the right-hand rule, and I will show you right now. So they tell you that the particles are moving this way, to the right. I'll just show you here. And now you know the magnetic field is out of the page. You have to kind of flip your hand over. So this is the magnetic field, this is the particles. And now your thumb, which you really can't see, but it would be directed to the bottom. Now that's the force your thumb is showing, so the electric field will now oppose that because it's going from positive to negative. So the electric field will actually go to the top, as shown here. Okay, now part B says, in terms of all the quantities, or any, of Q, B, E, and R, determine the expression for the following. B, the speed v of the charged particles as they enter region 3. So as they're entering region 3, they are exiting from region 2, which contains a magnetic and an electric field. So over here, part B. No, sorry, it has to focus. So if it has both the magnetic and electric field, they would have to be equal. So the force of the magnetic field equals the force of the electric field. The magnetic field has the value of Q, V, B, sine theta, and the electric field has a magnitude of Q, E. The Q's will cancel, and the sine theta would be 90, which would be 1, so you can cancel it. So basically you end up with V equals E over V. And we can leave our answers in that because those are both of them are acceptable expressions. Okay, C. The mass m of the charged particles. Okay, so we know that the force of the magnetic field is QVB. Now, this magnetic field is the centripetal force. So we can have centripetal force is mv squared over r. So now basically all we have to do is solve for m. So we have m equals r q v b over v squared. Then one of the v's will cancel, so we'll have r q b over v. And now that we have that, the v is actually, as you found here, e over b, so we can write that in. So r q b over e over b. So then when we simplify, we'll end up with r q b squared over e. And that's the mass of the charged particles. So now we have to do part D. Part D reads, the accelerating potential V in region 1. Okay, so going back to the diagram, this is region 1. Okay, so now they want the potential V. So what we could start with is basically just what work equals. So work, my physics teacher likes to say quite easily done, representing Q, E, D, quite easily done. It's just a way to remember. And then ED equals V, so you have QV. And then this is work, so kinetic energy equals 1/2 m. This is lowercase because it's velocity, and this is the potential. So now we just have to solve for this. So we get V equals 1/2 mv squared over Q. And we found from the part above that this is what m equals. So if we substitute and solve, we'll end up with 1/2 r q b squared over E times an extra Q. Oh, sorry, that's just, this expression is just M. Now we need a V squared, which is E squared over B squared. I have to divide by Q. Okay, there'll be a lot of simplification that will happen. And we'll basically end up with RE over 2. This is a potential V. Okay, moving along. Part E says, the acceleration A of the particles in region 3. Okay, so in region 3, as the question states, there's only a magnetic field. So, oh, sorry, hold on 1 second. Whoops. Okay, so in region 3, there's only a magnetic field. So if we were to do this, we'd have, I'll do it over here, E. Again, we start off by stating that the force of the magnetic field, which is QVB, is our centripetal force, so mv squared over r. And obviously, using Newton's second law, force equals ma. So now all we basically have to do is solve for a. So we have a equals QVB over m. And now we just substitute the values we know. We're allowed to keep Q. E we found is E over B. We have a B, and then M is RQB squared over E. So now when we cancel and solve for this, we end up with E squared over RB squared, because Q's will cancel and E goes to the top. Okay, now the final part. The time required for the particles to move along the semicircular path in region 3. Okay, so now they want the time for it to move around this circular path in region 3. So basically, we could say there's a formula for period, which is T equals 2 pi m over QB. But because this is a period for a full circle, but because we have a semicircle, we again have to divide by a 2. And the 2's will therefore cancel. Then we'll end up with pi times m. And m, which you've known from the previous parts, is RQB squared over E. And this is times QB. So the Q's cancel, one of the B's cancels, and we end up with pi RB over E. And that is the answer. But let's say you didn't know that, and we could go back to distance equals rate times time. The time equals distance over rate. The distance is 2 pi r, and then the rate, which is the speed, will be the velocity, which is E over B. Again, this is half a circle, so you have to divide by 2. If I divide, I will again end up with the same equation I had previously. Pi r times B over E. Both of them are the same. It's just whichever equation you remember. And yeah, so that's pretty much it. Hopefully this helps some of you, and yeah, talk to you later. Bye!